All right, so in chapter 6, we talked about probability in the context of how likely we are to get a certain score or proportion of scores or range of scores. Chapter 7 is going to get us closer to inferential statistics, using a sample to make a claim about a population by considering probability in the terms of samples, how likely we are to get a certain sample. And we do that by considering something called a distribution of sample means. So just to briefly review on z-scores and probability. So remember that we talked about that a location of a score in a sample or in a population can be represented by a z-score. And this is focused on single scores. What is the z-score for a certain raw score? But we don't, in statistics, typically use single scores because it's very likely that we can get some bizarre raw score from a population. We want to use larger samples because we can make more claims about a larger sample that is much closer in size to the actual population. Well, just like we can take any possible random raw score, possibly infinite number of different raw scores from a population, we can actually do the same thing with samples and their means. So what's neat is that we can pull a nearly infinite number of different samples of a certain sample size, n, from a population. And what a lot of these inferential statistics do is we take a certain sample's mean and convert it to a z-score, comparing it to all the other different possible random infinite samples and their means that we could pull from a population. So let's talk a bit of this concept called sampling error. So error doesn't mean, in this case, that there was a mistake. And when we talk about error in statistics, it does not mean error as a mistake. It means that something is just different than a mean or central tendency point. It's similar in concept to standard deviation. But sampling error simply says that sometimes when we pull a sample from a population, it's going to be a little bit different than the population. So we may pull, so let's say I measure all of your heights, and I take a sample, so there's 80 of you total. If I take a sample of 5, just by random chance, I could sample the 5 tallest people in the class, and that little sample would have a mean height much larger than the mean height of the whole class, the population. What we would call that is just sampling error. And this point is that samples are variable. I may pull from a sample of students testing their heights that I may pull just randomly a group whose mean is very low or very high. I might just randomly, by chance, pull a sample of a bunch of tall people or a bunch of short people. And so their means would be very different. But the likelihood, it's very likely that I will get a sample that's pretty close to the mean. And so this point here is that 2 samples are very much not often identical. You're not going to necessarily have the same makeup of people in the sample, the same standard deviation or mean of heights, or other variables. So how do we account for this when we take a sample and use it to make a claim about the population? Well, we have to create something called a distribution of sample means. So from this slide on, you need to pay very close attention to each point. So as we showed, the possible samples of all the infinite number of samples that we could get from a population, with the samples being a certain sample size, if it's a random sample, it's unlikely that we'd always pull samples that have the exact same sample means. With height, you may get a sample that's a little bit taller, you may get a sample that's a little bit shorter, or you may get one that's right around the actual population mean. But it's unlikely that these samples are all going to be the same in terms of their means. So we can do something. It's not something we specifically do or calculate when we do statistics, but it's something we conceptualize as this distribution of sample means. And simply all it is it's the collection of all possible random sample means that are of a particular size, sample size n, that can be obtained from a population. So essentially, the distribution of sample means does a few different things. You start by figuring out what's the sample size you're looking for. So n of 30. And the distribution of sample means considers first all of the possible random samples. Could be nearly infinite if it's a super large population. And that for each of those samples, each has a mean. And if you were to map them in a frequency chart, you could have a distribution of those, where the most common or highest frequency means for samples would be those pretty close to the population mean. But it's still possible to have sample means that are fairly different from the population mean. So with a sampling distribution, or distribution of sample means, what's important here is that it's slightly different from what we were talking about in previous chapters. Previous chapters talked about a distribution of scores, but a sampling distribution is a distribution of sample statistics, specifically our sample means. It's its own population that's related to the original population of raw scores. So to do this, again, we select all the possible samples of a certain sample size. So our one distribution, let's say we have all the possible samples of n equals 30 that we could get from a population. Here's a slide that goes into the process again. So essentially, you, in theory, would select one random sample of your specific sample size, calculate the mean, and plot it on a frequency distribution. And then you take another random sample with replacement, and you calculate the mean, put it in a distribution again. And you would repeat it for all the possible random samples of that particular sample size. And what's nice is that there are a few important characteristics. First, this distribution, the mean of the distribution of sample means, is the population mean. Because, return to a frequency distribution of scores, you're just more likely to pull scores in a sample that are closer to the mean. Thus, the mean of a distribution of sample means we expect is equal to the population mean. The distribution of sample means is approximately going to be normal in shape. And for the most part, that is regardless of whether the population of raw scores is normal or skewed or some other distribution. And also, the larger the sample size we think of, so if we do a sample distribution or sample mean distribution for super large samples, those sample means will in general be closer to the population mean. Why? It's because for each of those samples just requires more and more scores of the population for each random poll. So you're gonna have because there's a higher frequency of values around the population mean, you're gonna end up with larger samples pulling more and more of those highly frequent values. And so when you have larger samples, your distribution of sample means are going to be not much different, or in other words, have lower variance than distributions of sample means for smaller sample sizes. So something you can do on your own is, if we have this population of n equals 4, how would you construct a distribution of sample means for n equals 2? Well, what you do is you would take all the possible random samples of n equals 2. So you'd have 2 and 4. That's one sample. And then you'd have 2 and 6, another sample with a mean. And then you'd have 2 and 8 as another sample that has a mean. And then you do 4 and 6, and 4 and 8, and then 6 and 8. And you would get the means from each of those sample pairs, and if you plotted all those possible values, doesn't relate to this next slide, but this is what distribution of sample means would look like. So these are not related. Don't confuse that. Calculating a sample mean distribution would not lead to this. So if we have these sample means, if we go back to our empirical rule, or at least our rules regarding proportions, what can we say that the probability is that from a population of scores, you would pull a sample with mean greater than 7? Well, there's one circumstance, one possible mean that has a value greater than 7 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Be 1 out of 16. The probability of pulling a sample of mean greater than 7 is 1/16. So for inferential statistics, our goal is to answer probability questions about these sample means. If we had a 1 in 16 probability or proportion of getting a sample with a mean greater than 7, do we think that's a high probability, or is it not? If we were to get this, would we be confident in saying that that sample was drawn from that population? And that is the question of inferential statistics. So in terms of creating a distribution of sample means, we can't really do this in real life. So if I wanted to create a distribution of sample means for the heights of all UH students, that'd be insanely difficult to do. So we actually have this concept called the central limit theorem that we use to specify the shape, the central tendency, or the mean, and the variability of the distribution of those sample means. And for variability, we consider this concept called standard error of the mean. Remember, error is not a mistake. It's just a measure of discrepancy, or how different something is, similar to variability and standard deviation. And the standard error of M measures how well, typically, an individual sample mean represents the rest of the distribution. Essentially, how spread out are the different sample means. So for the central limit theorem, it's important to remember this is one of the most important concepts in statistics. So first, it applies to any population with mean, mu, and standard deviation sigma. The shape of the distribution does not matter. It can be normal, it can be skewed one way or the other, it can be bizarre looking shape, doesn't matter. It doesn't matter what the mean or standard deviation are specifically. The important rules here are that first, the distribution of sample means gets closer and closer to being a normal distribution the larger n gets. And no matter what, at about n equals 30, the distribution is going to be almost perfectly normal. And so if you have an n of 30 versus 31 versus 50 versus 100 versus 1,000, that's what your sample size is for all your possible samples that you pull from the population. The distribution of sample means will essentially be normal. But it's important to know that if you do have a population that is normally distributed, then your distribution of sample means, regardless of sample size, will also be normal. Second point for the central limit theorem is that this distribution of sample means for samples of size whatever size will have an expected value or a mean that is the same as the population. So the mean of the distribution of sample means is simply the mean of the population that the samples are drawn from. But different is the standard deviation or the standard error of the mean for the distribution. So what this will be is that the SEM, standard error of the mean, or in this case the standard deviation of the distribution of sample means, is the population standard deviation divided by the square root of the designated sample size of all those samples that you pulled. So in your distribution, it's all the samples of a particular size, one particular size, and of their means. And the standard deviation for that of the distribution of sample means is the population standard deviation, so of the raw scores, divided by the square root of that particular n sample size. We call that standard error of the mean. So we go through, talk about the important considerations, just go deep into them a little bit more so that you understand the distribution of sample means. So as I said previously, a distribution of sample means is almost perfectly normal. You can basically just count it as normal when, first, A, if the population of the raw scores that the samples are pulled from is also normal, or your N is at least 30, what we call relatively large, regardless of the shape of the original population you pulled the samples from. And then expected value of M, this is just what we call, this is another term for the mean. This is just what we expect the mean of the samples will be. That if we were to pull any random sample of that sample size from the population, the mean is what we would expect. The mean of the distribution of sample means is the value that we would expect any particular sample to have. Now that value of the mean for the particular sample may be different, but we expect it'll be a certain value. And so the mean of the distribution of sample means we call mu, or the mean of sample means, is equal to the population mean that you pulled those samples from. We call this a mean of means. So essentially it's the mean of the distribution of sample means. And this is unbiased statistic. Why? Because remember when we talked about how perhaps standard deviations are biased because they're based on, or excuse me, a sample standard deviation might be biased because of what values you pull from the population. This is just simply based on all the values of M. Means are unbiased. Therefore, we can say that the mean of the distribution of sample means is exactly the same as the population. Lastly, we're going to talk about the standard error of the mean. So typically we talk about how variable the distribution of scores is through standard deviation. Well, it's slightly different to get at the same concept for sample means. We use the standard deviation of the sample means. So we don't use the actual standard deviation, but we use it to calculate the standard error of the means. And the script it's written as sigma and subscript m. And you may also see it as standard error, SE, or SEM. In the journal articles that I write, I will typically use this term. This SE is common in workplace psychology, which is my area of research. But other places you may see SEM or these terms, the Greek symbols. And this provides us, in general, how much discrepancy you should expect, on average, between one particular random sample's mean and the population mean / mean of the distribution of sample means. So it's the average difference between one sample's mean and the population mean. All right, so just to get a little more technical on what the standard error of the mean is the basic definition is it's the standard deviation of the distribution of sample means. When this value is large, this means that the means of all the samples of size n that you pulled are very scattered. that there's a lot of difference between them. And it provides a measure of how much distance is expected on average between one particular sample mean and the mean of the distribution of sample means. So one sample and the distribution of all the samples. Or, as we talked about, the average distance between one particular mean, one particular sample mean, and the population mean. So that's where this gets really important, is this gives us a sense of how different one particular sample is from the population that we pulled it from, or that at least that we believe we pulled it from. And so to get a little more into what the size of the standard error means, we have this concept called the law of large numbers. So what it is that the larger the sample size that we're considering for our distribution of sample means, the greater likelihood or higher probability that any particular sample mean will be close to the population mean. Thus, in this case, when, as we talked about, when samples are very, very large, they have to pull more values that are very similar to the mean from the original population. Thus, these larger sample sizes will be much more similar to the population mean than samples that are much smaller. So the standard error should be smaller, or at least when you increase the sample size, that error should get smaller. And what's also neat is that when the variance in the population is smaller, remember the formula, standard deviation of population divided by the square root of the sample size. When the variance gets smaller for the population, it's more likely that the sample mean that you pull will be close to the population mean. And we can see that here. So remember our formula, standard deviation of the population divided by the square root of n. So we see here that if we have a standard deviation of the population of 10, if our sample size is 1, well, our standard error is 10. But if we have, say, a standard deviation, or no, excuse me, if you have a sample size of 25, which the square root of that is 5, 10 divided by 5 would give us 2. What we see here is that we're assuming that the population, no matter how large of samples we pull, it's always going to have the same standard deviation. But if we pull larger and larger sample sizes, that denominator, the square root of n, is just, with larger sample size, is going to get bigger and bigger and bigger, while that standard deviation of the population stays the same. So if that n gets closer and closer and closer to the actual population size, that standard error is going to get closer and closer to 0. And that would make sense, right? Because those massive samples, if they get infinitely large, will take up nearly all of the possible raw scores in the population. So there shouldn't be much different. Here we have just some visual description of, first, our original population of IQ scores, which IQ has a mean of 100 and a standard deviation of 15. Let's say we take here's one random sample we took, and it has, the labeling was incorrect here, should be S. We have a standard deviation here of 11.5. We have a mean of 101.2. slightly different, as we expect. But if we pull a whole bunch of sample size 25 IQ scores from this population, an infinite possible number, what we get is we get this distribution of sample means, with the mean being the same, 100, and the means do vary a bit. Like this one, this sample here is probably right about right here. It's probably pretty likely we get it. But we'd have a standard error of the mean of 15 divided by the square root of 25, which 15 divided by square root of 25 is equal to 15 divided by 5 equals 3. All right, so we talked about creating and thinking about a distribution of sample means, and why it's important to consider that one sample mean being particularly different or not different from the mean of the distribution of sample means or the population mean, why that's important. So how we use this is we can get into probability and z-scores, as we talked about in chapter 6, to consider what the probability is of selecting a certain sample with an expected sample mean, or the mean of our the distribution of sample means. And so just like we did for raw scores in a population, we can use the normal curve here to represent the probabilities, just like we did previously with, you know, a z-score between 0, or a z-score of positive 1, that of the raw scores, 34% or 34.13, I believe, percent of raw scores lie between the mean and positive 1 standard deviations. You can do exactly the same by computing z-scores for sample means, for each individual sample mean. So again, z-score for sample mean can be positive or negative. The number tells us the distance between the location of the sample mean and the actual mean of the distribution in standard error units. So for the distribution of sample means, z-score equals one particular sample's mean minus the distribution of sample means' mean, or population mean, divided by the standard error of the mean, or the standard deviation of the distribution of sample means. And so what we have here is, say we have a population that the mean of the population is 500, and subsequently the distribution of sample means for sample size n equals 25, that mean is 500 as well, based on the rules we talked about. And let's say we get to a standard error of the mean of 25. Well, we can have this question: what proportion of sample means have a value greater than 525? Well, 525 is one standard error of the mean value different from the mean of 500. So, using our empirical rule, as we discussed in chapter 6, we can add the 13.56%, I believe that was the number, I don't have them memorized, and plus 2.28%. Gets you about nearly 16%. So we could say that 16% of the sample, of the distribution of sample means, so 16-ish% of the sample means are greater than 525. So the same rules that we talked about in Chapter 6 work for the distribution of sample means. This slide here gets at what the distributions look like when n gets larger and larger. So we talked about as n gets larger, and we assume that the population standard deviation is always the same, regardless of the sample size you pull, that the standard error of the mean gets smaller and smaller. So for larger sample sizes, you have a very skinny normal curve. For very small sample sizes, you have a very wide normal curve. And this should make sense because, as we talked, when sample sizes get closer to the actual population size, they're going to get more and more reflective of the actual population. Whereas for small sample sizes, you're more likely to get sample means that get at extreme values of the population. So these distances far from the mean here will have some bit of frequency that's greater than over here for the same value. So that's about it for what you need to know for distribution of sample means. But briefly, let's talk about what this means for inferential statistics, because the next chapter that we will discuss, so for next week, will be our first inferential statistics chapter, an introduction to hypothesis testing. So for inferential statistics, what we're using sample data to make claims about the population. But as we know here, sample information is not always perfectly related to the population. Sometimes we just get sampling error. We have a mean that's just a bit different than what the population's is. So what's tough is that the differences between a certain sample and the actual population that it comes from introduces uncertainty. Can we be certain that this sample truly is from the population? Or is it from a slightly different population? If I were to pull a sample of students from the class that you're all in, can we say that it's from a population of UH students? Technically, yes, but it's fundamentally different because you're all taking classes that are part of the psychology program. There are some students that never take a psychology course. So we can only say so much that students in the course here reflect the students in the entire population of UH students. We may be better at saying that you students in this class are more reflective of psychology majors at UH. And so the statistical techniques that we use essentially define how highly or not highly probable it was that we drew a particular sample from that population. So let's say we have this sample here, or this population and sample here, and this population has a mean of 400, a standard deviation of 20. Don't worry about what we're measuring or what the treatment is. Let's say we take a sample of 25 rats. We'll call them rats that we're doing some sort of medical treatment testing on. Give them a treatment. Does this treated sample reflect the population still? The population as a whole didn't get the treatment. What we do with inferential statistics, if we give a sample a treatment, we say, what is the probability that they're still part of this population after the treatment? So we could say that, did the mean of this sample go to such a different value that the likelihood of it still remaining part of this untreated population is a certain value. If the mean of this sample is still pretty close to this mean, we could say that the treatment had no effect, and that this sample still reflects the population. But if the treatment leads to a sample mean on some value that is way different now from this value, then we could say that this is no longer a sample from this population. It's a sample for a theoretical population of rats that received this treatment. And how do we use what we've discussed to determine whether it comes from if we can count it as part of the same population or part of a new population? Is basically using z-scores. So take the mean of this and compare it to this distribution of sample means for the original population. Remember, we talked about we're confident, we can be super confident that a value came from the population if it's in the middle 95% of values and not from the lower 2.5 or higher 2.5, what we call an alpha value. We'll describe that more next time. If the mean falls in between z-score of negative 1.96 or positive 1.96, which those are the z-scores that correspond to 95% of the values being right in the middle, in between those z-values. If that z-score, for whatever the new mean is, lies in here, we can be confident in saying that we can't say that it's different from the population. But if that z-score lies in one of these extreme values, then we can say it's so unlikely that if this treatment didn't work, that we would have just pulled this sample by chance. That we just somehow got a biased sample. It's so unlikely that we can say that that sample is from a different population. And that, in essence, is the concept of inferential statistics. And we'll go into actual testing procedures, the numbers of it, next week. All right, if you have questions about any of the concepts we talked about this week, this is a very theoretically dense chapter. It's quite a step up from what we had talked about in chapters 1 through 5. If you're struggling, please reach out to me. We can set up a meeting, help you figure out what this is all about, because this is the link that takes from what we've talked about into inferential statistics. And it's important that you understand this material. All right. Quiz will be posted along with these videos and the PowerPoints. And again, please get in touch with me if you need.